According to Article 430.22 of the National Electrical Code, the ampacity of service conductors for motors with a nameplate rating of 100 horsepower or more shall be calculated based on the motor's locked rotor ampacity. The locked rotor ampacity was not provided in the supplied information, but it can be estimated as approximately 6 times the rated full load current. The estimated locked rotor ampacity is 6 times 645 amps, which equals 3,870 amps. Based on the estimated locked rotor ampacity, the service conductors should be rated for a minimum of 3,870 amps continuous. Since the system is rated for 150% overload capacity, the service conductors should be upsized by 50% to account for the peak load. The upsized service conductor ampacity is 3,870 amps times 1.5, which equals 5,805 amps. Therefore, the recommended service conductor size is 750 mcm copper conductors, which have an ampacity of 600 amps. The duty cycle for the motor is not explicitly stated in the provided information. However, it is mentioned that the system is rated for 150% overload capacity for 60 seconds once every 5 minutes. This suggests a duty cycle of 10%, that is 60 seconds out of every 5 minutes, or 0.1. According to NEC Article 430.22e, for motors with a duty cycle less than 100%, the current rating of the overload device, which is a reverse feed rated overcurrent device in this case, can be adjusted by multiplying the continuous current rating of the motor by the square root of the duty cycle. The adjusted current rating is the motor continuous current times the square root of the duty cycle. The adjusted current rating is 645 amps times the square root of 0.1, which equals 202 amps. Therefore, the overcurrent device should be rated for a minimum of 202 amps. To further elaborate on service conductor sizing for AC dynamometers, we need to delve deeper into the NEC requirements and practical considerations. Firstly, let's break down the key NEC articles relevant to this application. Article 430 covers motors, motor circuits, and controllers. Within Article 430, specific sections address conductor sizing based on motor nameplate ratings, locked rotor current, and duty cycles. When dealing with motors of 100 horsepower or more, as in this case, the NEC emphasizes using the locked rotor ampacity for initial conductor sizing. The locked rotor ampacity represents the current the motor draws when it's initially starting, which is significantly higher than the full load current. The calculation we performed, estimating locked rotor ampacity as 6 times the full load current, is a common rule of thumb. However, it's crucial to consult the motor's specific nameplate data or manufacturer's specifications for the actual locked rotor ampacity value. Using the exact value will provide a more accurate and safer conductor sizing. Now let's discuss the 150% overload capacity requirement. This means the system must be able to handle 1.5 times the full load current for a short duration, specifically 60 seconds in this scenario. To accommodate this overload, we upsize the service conductors by 50%. This ensures the conductors can handle the increased current without overheating or causing voltage drop issues. It's important to note that the NEC provides tables and guidelines for conductor ampacity based on insulation type and installation conditions. When selecting 750 mcm copper conductors, we reference their ampacity rating of 600 amps. This rating is typically based on a specific temperature rating, such as 75 degrees Celsius or 90 degrees Celsius. Ensure that the conductors are installed in a manner that allows them to dissipate heat effectively, as diluting factors may apply if they are installed in conduit or enclosed spaces with limited ventilation. Next, let's explore the duty cycle aspect. The duty cycle, as we calculated, represents the percentage of time the motor operates at its overload capacity. In this case, the motor operates at 150% load for 60 seconds every 5 minutes, resulting in a 10% duty cycle. The NEC allows for adjusting the overload protection based on the duty cycle. This is because the motor and conductors have time to cool down during the periods of reduced load. By multiplying the continuous current rating of the motor by the square root of the duty cycle, we obtained an adjusted current rating of 202 amps for the overcurrent device. This allows us to select a smaller overcurrent device, which can provide better protection against overloads and short circuits without nuisance tripping during normal operation. It's essential to understand the difference between overload protection and short circuit protection. Overload protection is designed to protect the motor and conductors from prolonged overcurrent conditions, such as those caused by mechanical overload or voltage imbalances. Short circuit protection is designed to quickly interrupt the circuit in the event of a short circuit fault, which can cause very high currents and potential damage. The overcurrent device we selected, rated for 202 amps, provides overload protection. A separate short-circuit protective device, such as a fuse or circuit breaker, should also be installed to provide short-circuit protection. The short-circuit protective device should be sized according to the NEC guidelines and should be capable of interrupting the maximum available fault current at the installation location. In addition to the NEC requirements, it's also crucial to consider the specific application of the AC dynamometer. An AC dynamometer is used to test the performance of other motors or equipment. It acts as a generator, converting mechanical energy into electrical energy. This means the dynamometer can also feed power back into the electrical system. Therefore, the overcurrent protection must be rated for reverse feed applications. This ensures the overcurrent device can properly interrupt the circuit when power is flowing in the reverse direction. When selecting service conductors, it's also essential to consider voltage drop. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause the motor to operate efficiently, overheat, or even fail. The NEC recommends limiting voltage drop to a maximum of 5% for motor circuits. To calculate voltage drop, you need to know the conductor length, current, conductor size, and conductor impedance. There are online voltage drop calculators available that can help you perform this calculation. If the calculated voltage drop exceeds the recommended limit, you may need to increase the conductor size or use a different conductor material with lower impedance. Furthermore, consider the environmental conditions in which the conductors will be installed. Factors such as ambient temperature, humidity, and exposure to corrosive substances can affect the conductor's ampacity and lifespan. The NEC provides deterring factors for conductors installed in high-temperature environments or exposed to corrosive substances. Make sure to apply these deterring factors when selecting conductors to ensure they can operate safely and reliably under the given environmental conditions. Finally, it's always recommended to consult with a qualified electrical engineer or electrician to ensure that the service conductors and overcurrent protection are properly sized and installed according to all applicable codes and standards. They can perform detailed calculations, consider all relevant factors, and provide expert guidance to ensure the electrical system is safe and reliable. Let's recap the key steps for selecting service conductors for an AC dynamometer application. Firstly, determine the motor's full load current and locked rotor ampacity. Secondly, calculate the required conductor ampacity based on the locked rotor ampacity and overload requirements. Thirdly, select conductors with an ampacity equal to or greater than the calculated value, considering insulation type, installation conditions, and deterring factors. Fourthly, calculate the voltage drop and ensure it's within acceptable limits. Fifthly, select an overcurrent device rated for reverse feed applications and sized according to the duty cycle. And sixthly, ensure the installation complies with all applicable codes and standards. By following these steps, you can ensure that the service conductors and overcurrent protection are properly sized and installed, providing safe and reliable operation of the AC dynamometer. I want to elaborate further on the practical aspects of implementing these calculations and recommendations in a real-world industrial setting. Firstly, let's talk about the importance of accurate data collection. The entire process hinges on having accurate motor nameplate information, including the full load current, service factor, and if available, the locked rotor ampacity. Often, in older installations or when dealing with refurbished equipment, nameplates can be damaged or illegible. In such cases, it is crucial to consult the motor manufacturer's documentation or use reliable databases to obtain the correct specifications. Guessing or estimating based on similar motors can lead to significant errors and potentially unsafe conditions. Secondly, consider the impact of harmonics on conductor sizing. Modern industrial environments often have a significant amount of nonlinear loads such as variable frequency drives, electronic ballasts, and switching power supplies. These loads generate harmonic currents, which can increase the heating of conductors and transformers. The NEC requires derrating conductors when harmonic currents are present. The amount of derrating depends on the total harmonic distortion and the type of load. It is essential to perform a harmonic analysis to determine the appropriate derrating factor. Thirdly, pay close attention to the conductor's temperature rating and the ambient temperature of the installation environment. Conductors are typically rated for 60 degrees Celsius, 75 degrees Celsius, or 90 degrees Celsius. The ampacity of a conductor decreases as the ambient temperature increases. The NEC provides tables that specify the ampacity derrating factors for different ambient temperatures. It is crucial to select conductors with a temperature rating that is appropriate for the installation environment and to apply the necessary derrating factors. Fourthly, carefully consider the conductor installation method. The way conductors are installed can significantly affect their ampacity. Conductors installed in conduit, especially when bundled together, will have a lower ampacity than conductors installed in free air. The NEC provides tables that specify the ampacity derrating factors for different installation methods. It is essential to select the appropriate installation method and to apply the necessary derrating factors. Fifthly, ensure proper grounding and bonding. Grounding and bonding are essential for safety and for preventing electrical noise. The grounding conductor should be sized according to the NEC and should be properly connected to the grounding electrode system. Bonding conductors should be used to bond all metal enclosures and equipment together to create a low impedance path for fault currents. Sixthly, implement a robust maintenance and testing program. Electrical systems should be regularly inspected and tested to ensure they are operating safely and reliably. This includes visual inspections of conductors, connections, and equipment, as well as electrical tests to measure voltage, current, insulation resistance, and ground impedance. Any problems that are identified should be promptly corrected. Seventhly, document all calculations and decisions. It is crucial to document all calculations, assumptions, and decisions made during the design and installation process. This documentation will be invaluable for future maintenance, troubleshooting, and upgrades. It will also help to demonstrate compliance with the NEC and other applicable codes and standards. Eighthly, provide adequate training for personnel. Personnel who work on electrical systems should be properly trained in electrical safety, the NEC, and the specific equipment they are working on. Training should be ongoing and should be updated as codes and standards change. Ninthly, use appropriate personal protective equipment, PPE. When working on electrical systems, it is essential to use appropriate PPE, such as safety glasses, gloves, and arc flash suits. The level of PPE required depends on the voltage and current levels and the potential for arc flash. And tenthly, follow lockout tagout LOTO procedures. Before working on any electrical equipment, it is essential to follow LOTO procedures to ensure that the equipment is de-energized and cannot be accidentally energized. This includes disconnecting the equipment from all power sources, locking out the disconnect switches, and tagging the disconnect switches to indicate that the equipment is being worked on. By following these practical considerations, you can ensure that the service conductors and overcurrent protection for your AC dynamometer are properly sized, installed, and maintained, providing safe and reliable operation for years to come. I want to emphasize the importance of understanding the nuances of applying the National Electrical Code, NEC, particularly in specialized applications like AC dynamometer systems. The NEC provides a comprehensive framework for electrical safety, but its application often requires interpretation and judgment based on the specific characteristics of the installation. Firstly, let's revisit the estimation of locked rotor ampacity, LRA. While using a multiple of the full load current, FLC, like 6 times FLC, is a common starting point, it is not universally accurate. The actual LRA depends on the motor's design and can vary significantly between different manufacturers and motor types. For critical applications, it is always best to obtain the actual LRA from the motor's nameplate or manufacturer's data sheet. If the LRA is not readily available, consider using a more conservative multiplier or consulting with a motor specialist to determine a suitable value. Secondly, consider the impact of the supply transformer on the available fault current. The available fault current at the motor terminals is determined by the impedance of the supply transformer and the upstream electrical system. A larger transformer with lower impedance will result in a higher available fault current. The overcurrent protection devices must be able to interrupt the maximum available fault current to prevent equipment damage or personal injury in the event of a short circuit. It is essential to perform a fault current study to determine the available fault current at the motor terminals and to select overcurrent protection devices with adequate interrupting capacity. Thirdly, pay attention to the coordination of overcurrent protection devices. Overcurrent protection devices should be coordinated to ensure that the device closest to the fault will trip first, minimizing the extent of the outage and preventing unnecessary tripping of upstream devices. This is typically achieved by using time current curves to compare the tripping characteristics of different overcurrent protection devices. The time current curve should be coordinated to ensure that the downstream device trips before the upstream device for all fault current levels. Fourthly, consider the impact of voltage fluctuations on motor performance. Voltage fluctuations can affect motor performance and can lead to overheating or premature failure. The NEC requires that motor circuits be designed to accommodate voltage fluctuations within a specified range. It is essential to monitor the voltage at the motor terminals and to take corrective action if voltage fluctuations exceed the acceptable limits. This may involve installing voltage regulators or upgrading the electrical supply system. Fifthly, pay attention to the requirements for motor controllers. Motor controllers are used to start, stop, and control the speed of motors. The NEC specifies requirements for motor controllers, including the type of controller, the size of the controller, and the overcurrent protection requirements. It is essential to select a motor controller that is appropriate for the motor and the application and that complies with all applicable NEC requirements. Sixthly, consider the impact of regenerative braking on the electrical system. AC dynamometers often use regenerative braking, which means the motor acts as a generator and feeds power back into the electrical system. This can create challenges for the electrical system, as it must be able to absorb the regenerated power without causing voltage fluctuations or other problems. It is essential to carefully design the electrical system to accommodate regenerative braking and to use appropriate overcurrent protection devices that are rated for reverse current flow. Seventhly, pay attention to the requirements for surge protection. Motors and motor controllers are susceptible to damage from voltage surges caused by lightning, switching operations, or other disturbances. The NEC recommends installing surge protection devices, SPDs, to protect motors and motor controllers from voltage surges. SPD should be selected based on the voltage and current levels of the electrical system and should be installed in accordance with the manufacturer's instructions. Eighthly, consider the use of energy-efficient motors. Energy-efficient motors can save significant amounts of energy and reduce operating costs. The NEC encourages the use of energy-efficient motors and provides guidelines for selecting and installing them. It is essential to consider the energy efficiency of motors when designing and installing motor circuits. Ninthly, pay attention to the requirements for labeling and documentation. The NEC requires that electrical equipment be properly labeled and documented. This includes labeling conductors, overcurrent protection devices, motor controllers, and other equipment. It is also essential to maintain accurate documentation of the electrical system, including wiring diagrams, equipment specifications, and test reports. And tenthly, stay up to date with the latest NEC requirements. The NEC is updated every 3 years, and it is essential to stay up to date with the latest requirements. This can be achieved by attending training courses, reading industry publications, and consulting with qualified electrical professionals. By paying attention to these nuances and by carefully applying the NEC requirements, you can ensure that the electrical system for your AC dynamometer is safe, reliable, and efficient. Remember, the NEC is a living document that is constantly evolving to address new technologies and safety concerns. Continuous learning and professional development are essential for electrical professionals to stay at the forefront of the industry and to provide the best possible service to their clients.